Okay, welcome back everyone. So we are about to start the last module of the course, which is the which I feel is one of the most important topic of this is one of the most important topic I would say of this course. It's known as hydrodynamic instabilities, or you can also call it as hydrodynamic stability, uh, or uh, or like whatever way you want. But the reason why I feel this is one of the important aspects of fluid mechanics in principle, viscous fluid flows, is that it has a very rich application, starting from fundamental fluid mechanics problem to many real life applications, to name a few. Okay. So what we'll see is so as you have seen in the lecture series of this week, we were introduced to something known as the stability of viscous parallel flows, where you basically derived something known as the Orr-Sommerfeld equation, which governs how the disturbances basically vary along the flow field, when your base state, or so we'll see what the base state is, but when your initial state, as you can say, or when your unperturbed state is being disturbed, or we'll call the word perturbed by some perturbations. Okay. So yeah. So the agenda for this week and the subsequent week, because we will be, so this is the last module, so these are the topics which are left to discuss uh, uh, for this for the discussions hours that we are having. So what we'll be doing is, so in class you have, or in the discussion, sorry, in the lecture series, you have typically learned something known as stability of viscous parallel flows. So what we'll do is we will quickly brush up the concept of stability by learning stability of inviscid parallel flows, which is a special case of the viscous parallel flows when typically the fluid viscosity is basically equal to zero. Okay, and we'll be looking into parallel flows, and this same framework can also be applied to nearly parallel flows. Nearly parallel flows means that the predominant velocity of the flow field is in the direction of the, I mean, it's basically along the direction of the flow field itself. Uh, so so those flows are kind of like nearly parallel flows. Uh, and what we'll do is we will try to learn the aspect of stability analysis by looking into the stability of, as I said, of inviscid parallel flows, and we will derive something known as the Rayleigh stability equation. That is the objective, that is the overall ultimate objective of the exercise that we'll be starting today. And hopefully we'll be finishing it by next week, because it's a little bit of a long problem that we'll solve. And once we know how did you derive the Rayleigh stability equation, we will then compare it with the Orr-Sommerfeld equation that you have derived for viscous parallel flows. And then you will basically realize that when Reynolds number is equal to zero, and if you substitute that in the Orr-Sommerfeld equation, you will simply get back the Rayleigh stability equation. So it will be a good practice for us to derive the Rayleigh stability equation, because this is a little bit of a simplified form of or it's a simplified case of a Orr-Sommerfeld equation when the fluid viscosity is zero. Okay. So that's the idea. So once we derive the Rayleigh stability equation, we will also look into certain aspects, that how can the Rayleigh stability equation assess the stability of a certain base flow. So for that, we'll be looking into certain criterias, and we will in principle discuss three criterias, which is known as, so the first of one is known as the Rayleigh inflection point criteria. The second, we will see that the Rayleigh inflection point criteria is not, sufficient for assessing the stability of a given base flow. So what we'll see is we'll then look into a more stronger criteria, which is known as the Jortov's criteria, and then also we'll look into something known as the Howard semicircle theorem to end the assessment of the stability of a given base flow. Okay, so that's the idea. So these are all the things that we'll be discussing in this module of stability analysis. So we'll start off by looking into uh, a very simple base flow, and what basically and what adding something known as the disturbances or the perturbation brings in new to the given base flow. And we of course will be looking into the equations which governs this disturbances, and finally we'll see that how do we take the solution of these disturbances to what we call as the normal mode analysis. So we will basically look into that, and yes, and then ultimately solving for the normal mode to what we call it as the eigenvalues and the eigenfunctions to obtain an equation which governs the which governs how which govern the stability of which eventually govern the stability of inviscid parallel flows. Okay. All right, so let's get started. So what we'll do is we'll solve a similar. So we'll start off with a similar problem that we have solved in class, albeit that now the case is of an inviscid parallel flows, as you can see, for which you can assume. I believe you have got the sense that now instead of solving the Navier-Stokes equation, we will basically solve the simplified form of the Navier-Stokes equation, which is the Euler's equation. Okay, so that's what we will solve, and then the overall steps are the same, and we'll assess the stability of the given base flow. Okay, so just to frame the problem and to be familiarized with the physical paradigm, what we have is we have a channel, okay, as you can see, and there is a flow that is taking place along the axis of the channel, which is in the x direction, and the and this flow, that the flow in blue that I have shown here, this we will consider it as the base flow. Okay, base flow means that it's the unperturbed, or sometimes we also call it as the unperturbed flow. Is that the flow which exists without adding any perturbation is something we'll describe it as the base flow. Okay, so you can see that the base flow, and more importantly, what we'll do is we'll first we'll first clarify the notations in this module. So what we'll do is, only for this module we will denote all dimensional quantities by start. Okay, so I will just clarify, basically moving on into the going ahead with the numerics. First of all, let's clarify certain notations. Okay, so what we'll do is any variable with a star. Okay, so in principle, any lowercase variable with a star, we'll call it as my total variable. Okay, and things will be clear when we go ahead, like why this is called as a total variable and what does it consist of. So for instance, if I call some variable as my total variable, this will include the base variable. So this will include the base variable plus the perturbations. Okay, and I shall denote this total variable as a lower cap letter with a star, because star means things are dimensional. Okay, then this then means that I will denote all my base variables as an uppercase letter with a star, which where again star means dimensional. So an uppercase variable is basically my base variable. Okay, and if that is the case, then I also need a notation for the perturbations. So what we'll do is any lowercase variable with a dash in it, we will call it as the perturbations. Okay, and the stars that you can see here, this denotes that the quantities are dimensional. For example, if we want to derive a non-dimensional version of these variables, I would simply say that a is my total non-dimensional variable, capital A is my total non-dimensional base variable, and a dash is my total total non-dimensional perturbed variables. Okay, that's so these notation we will stick, we'll stick to it throughout the analysis of stabilities, or throughout the stability analysis, and we will follow this notation in principle. Okay, so then it means that then from this picture we can see that we have a base flow which is denoted by capital U, and it seems that the base flow is just varying along the z direction, as you can see from here, and the direction of this flow is along the x direction. Okay, and you must realize that everything about the base flow is known to us. So what we seek is that, we given a base flow, what it means is that, okay, I have a known base flow. The question that we seek in perturbation analysis or stability analysis is that, if we add a small disturbance to this base flow, how will the disturbance evolve? Okay, will they grow with time, will they decay with time, or will they, or it's like, will they remain constant with time? That is something which we call it as the marginal stability, or sometimes they also use something known as the neutral stability. But anyways, these are the three questions that we seek. So this then means that we are only interested in finding out the perturbations. Okay, so if we are interested in finding out the perturbation, this means that the entire knowledge of the base flow should be known to us. That means that this uz should be known to us, and this capital P should also be known to us. Okay, so we will call it as the base flow and the base pressure, okay, in this analysis. Now what we'll do is, this is something that we have seen in the lecture series as well. So we will be staying into the realm of something known as the linear stability analysis. Okay, so we will be, so I'll write it down. So we shall be performing linear stability analysis. Okay, so what it means is that, so by the word linear stability analysis means is that the magnitude of the perturbations are less compared to the magnitude of the base flow. Which means if I, let's say, have a perturb variable V star prime, the magnitude of this perturb variable is very much less than the magnitude of the base flow. Okay, where the base flows are denoted by capital V basically. Okay, so this is what is meant by, so in principle this condition, so this condition needs to be satisfied if we are to perform linear stability analysis. Okay, so this condition needs to be satisfied. Okay, so two things we have learned. First is the notation, that given a base flow, how we'll denote the base variable, the total variable, and the perturbations. And the second thing is that we will be performing something known as the linear stability analysis, which in principle means that the magnitude of the perturbed variable will be less than the magnitude of the base variable. Okay. So with then, let's formally start the problem. So we'll be starting off with writing the assumptions, because this is important uh, with respect to the analysis that we are going to do. So we'll be starting off by writing the assumptions of this problem. Okay. So the first assumption is that, as I said, we are assuming that the flow is inviscid. Okay. So that's the first assumption. So it's an inviscid flow, and we will be assuming that, so in principles throughout this course we are assuming that the flow is incompressible. So here also it is no exception. We'll consider that the flow is incompressible. Okay, so it's an inviscid flow and it's an incompressible fluid. Okay, the second thing is important, that is, so I said that the knowledge of the base flow should be known to us if we want to see how the perturbation, if we want to actually solve the problem for the perturbations, which means that base flow properties are known to us. In fact, this is not an assumption, this is actually a statement, are known. And here we will say that the base flow, and since it is known, we will say here that the base flow is unidirectional. Okay, and we can also then, it's an addition to this statement. We can also assume, in fact we are to assume that the base flow is steady. Okay, which is the case that we'll be seeing that we are actually trying to see in this picture. For instance, this u of z. Okay, if this is basically the base flow, you can see that this is unidirectional, yes, from the profile, and also you can see that this u is just a function of z, which means it is not a function of x, it is not a function of y, it is also not a function of time, which means that the base flow is also steady. Okay, all right, so then let's get started. So what we'll do is, the first step of stability analysis is that, see, you should always be clear with the objective, that what actually the broad picture that we are looking to, that we are trying to look or trying to assess in this study. So we are actually trying to find out how the perturbations behave. So if we add some disturbances to the flow, how will the disturbances behave? So ultimately we want equations that, so in order to know the behavior of the disturbances, we must write equations, okay, that govern these disturbances. And in order to write equations that govern these disturbances, we must first write equations that govern the total variable. Okay, and in principle what we'll do is, we will see that, okay, these are the equations that govern the total variable, for instance the total velocity and the total pressure. Then what we'll do is, the base flow equations are trivially known to us, because the entire knowledge of base flow is with us. What we'll do is, we will take the equations of the total variable, we'll subtract the equations of the base flow to basically get the equations of the perturbations. But more importantly, we'll be sticking our analysis in the regime of linear stability analysis. Okay, so as so we will see later that what we'll do is we'll basically, after deriving the equations for perturbations, we will linearize those equations to derive, equations for perturbations in the regime of linear stability analysis. So this is the roadmap that we'll follow. So as I said, then the first step of this roadmap involves, writing the governing equations for the total variable. Okay. So step one is governing equations for total variables. Okay. And by total variable, I will have my velocity v star, that is my total velocity. And remember, this total velocity will be a function of position, or will be a function of the coordinates, that is x bar star. For instance, x is basically the position vector in the flow field, and it will also be a function of time. Okay. And also remember, we also need to solve for a total pressure, which is P star, and this will also be a function of x bar star and time. Okay, so these are the total variables for which we are going to write equations, and at least we now know that the first equation is going to be our continuity equation. Okay, which is nothing but the divergence of V star is basically equal to 0. And I reiterate, the start quantities means dimensional. Okay, and later on we'll be actually choosing characteristic variables to eventually non-dimensionalize the governing equations. Okay, so so the first equation that governs the total variable is the continuity equation. The second equation, we know that since the flow is inviscid, we have at us the Euler equation, which is basically what? So this is a vector. So it is del v. Okay, so this, remember, this v is a small v because this denotes the total variable. Okay, so this is del v star by del t. Okay, plus v dot grad v star dot grad of v star. Okay, and this is equal to minus grad of v star. Okay, so that's it. That's the continuity equation written for the dimensional total variable. Okay, and this is the Euler equation written for, again, the dimensional velocity and the dimensional pressure. Okay, and then let us be clear about the fact that this v star, this small v star, this consists of the base profile. And remember, this small v star, as I said, is a function of space in general, and it is also a function of time. And this can be written as, see, the total variable, as I said, can be written as the base variable. So the base variable is u star of z star ex plus the perturbations, which is v star prime of x star comma t. Okay, so as I said, and as I was repeatedly telling in from the previous 5-10 minutes, is that, so this is the total variable, as I say. This is my base flow profile, or I will call it as the base variable, and this is nothing but the perturbations for which eventually we are trying to solve, and eventually we are trying to look into the equations that govern these perturbations. Okay, so this is my perturbations. Okay, similarly, just like the velocity, you can also write the total pressure, which is a function of x star, x bar star, and t, as the base pressure, which is p star. Okay, plus the perturbations in pressure, which is p star prime, x star, and t. Okay, and maybe I'll name this equation S3a and this S3b. So just for a recap, what we are doing is we have written the equations that govern the total variable, and then we have written the total variable as the base variable plus the perturbations. That's all that we have done here. Okay, so then what we will see that, see, our objective is, as I said, our objective is to find the equations that govern the perturbations. So if we have the equations that govern the total variable, and somehow if we subtract the equations that govern the base variable, we will eventually get the equations that govern the perturbations. Okay, that's the idea. Okay, so now what we will see that, does the base variable satisfy this equation. Okay, so this is something that we must ensure first in order to derive equations for the perturbations. Okay, so the question that we will seek, that we are trying to seek now is, thus the base variable satisfy the governing equations. And let's see if they do or not. For instance, if I just write the continuity equation for the base variable, so the continuity equation is going to just give me what? It is just going to give me divergence of capital V star is equal to 0, and then I can then write it as del Q star by del X plus del V star by del Y plus del W star by del Z is equal to 0. But we know that for the base variable is unidirectional, which means that V star is just equal to 0 and W star is just equal to 0. Why? Because the base variable is unidirectional, which then means that my del U star by del X is equal to 0, and this is indeed the case because we already saw that U star is just a function. So this is just a function of Z only. Okay, which means that this condition that del U star by del X is equal to 0 is trivially satisfied. Okay, all right. The second equation, if we now look for the base, for the base variable, is what is the Euler equation. So if we just write the Euler equation now, and here we'll just so as we saw that we just have one non-zero component of the base variable, which is just the x directional velocity. So we'll just write Euler's equation in the x component only, because the other two components are just 0, because v and w for the base variable is equal to 0. So if we write Euler equation in the x direction for the base variable, remember this is only true for the base variable. We cannot make this statement for the perturbations, because in general the perturbations are going to have component in the x, y and z, and those components individually will also vary along the x, y, z and time space basically. Okay, but this is true only for the base variable, because as I said, the information about the base variable is in our hand, and this is how we have chosen the base variable basically. Okay, so if we write the Euler's equation in the x direction, it just turns out to be del U star by del t. But remember, del capital U star by del capital U star is just a function of z. This is something that we need to understand. And then we have del U star of z times del U star of z by del x. And the other terms will anyway be going to 0. So this is 1 upon rho times del p star by del x. Now, we know that this term is 0 because the base variable is steady. This is something that we have assumed. And we also know that U star of z is just a function of x, which means this is equal to 0. Which then means that del capital P star is going to be stars. Okay. Star is also going to be star. So del capital P star by del x star is equal to 0, which means that my base pressure is not a function of x. See, even though we have a velocity field in the x direction, in inviscid fluid you can prove that if the velocity field is in the x direction, let's say, and of course it is incompressible and steady, if we are looking in the inviscid limit, pressure will always be constant. And I'll try to physically explain you why this is the case. But first let us just write it down, and let us formally write it down that P star is just a constant, and we will call it as some P0. So what does it mean? It means that my base pressure that we have chosen, that is PB, or let's say capital P star, this is just equal to some constant which is equal to P0. See, this is the scenario that is simply because the fluid is inviscid. Okay, had it been a viscous fluid, then we will eventually see that this gradient of pressure is being balanced by the viscous term. But here, since the viscous term is 0, the pressure gradient itself has to be equal to 0 in order to satisfy the Euler equation in principle. Okay, so had this flow been inviscid in nature, okay, then P star would not be equal to constant. In fact, then gradient of pressure, then the viscous term del square of V is itself being balanced by the gradient of pressure. But since here the del square V term is 0 owing to the fact that the viscosity of the fluid is 0, this means that the gradient of pressure, that the pressure gradient in an inviscid fluid is always equal to 0, which means, I mean, I should be more careful. I should tell that the pressure gradient in a inviscid fluid which is steady and flowing, let's say in a particular direction, the pressure gradient is 0, which means that pressure will be constant throughout. Okay, so this is the idea. But remember, had this been a viscous fluid, you cannot say that your base pressure is going to be equal to constant. So this is the consequence of the flow being inviscid in nature. Okay, so that's it. So this means, so what does it mean? This then means that my base variable, that is uz, capital U star z, and my base pressure P star, which is just a constant, they trivially, this means that, so they trivially, so these base variables, so I'll write it down. So these base variables trivially satisfy the governing equations. Okay, all right, then our task is to find out equations which governs the perturbations. Okay, and that is, and since we are basically trying to look into the behavior of the perturbations, as I said, we must first find equations which govern these perturbations. Okay, but before that we'll be doing an important step, which is nothing but non-dimensionalizing the system. Okay, because it gives, it makes our life easier if we actually solve this problem non-dimensionally. Okay, so we'll be non-dimensionalizing the equations, okay, for which, as we saw multiple times, at least up to this point, we have to choose certain characteristic variables. Okay, so first of all, the characteristic length, which we call it as LC, and this is something that we have been doing repeatedly, we'll choose this as the channel height h, because for this channel, there is a given height. I think I have not written it, but there is an inherent length scale of this channel, which is 8, which is the height of the channel. Okay, that's the length scale. Now the velocity scale, or basically the characteristic velocity, we will call it as UC. And what are the possible choices of this characteristic velocity? So given the base flow is known, we can either choose the maximum of the base flow profile, the maximum of U star of Z star, or average of U star of Z star as my characteristic value, as my characteristic velocity, and any one of these two are perfectly fine with us. Okay, so this then becomes my characteristic velocity, and then couple of other characteristic variables are also needed to be determined. For instance, the characteristic time scale, which we call it as TC, then this then becomes equal to the characteristic length scale by the characteristic velocity, and then this becomes h by either max of uz or average of uz, where uz is basically the base flow profile. Okay, and similarly we will choose my characteristic pressure as, the choice of the characteristic pressure is trivial because now this is an inviscid fluid, so we cannot choose the viscous scale for pressure. So we will choose my characteristic pressure as rho times of the characteristic velocity squared. Okay, all right. So I hope things are clear up to this point. Okay, so just to reiterate what we did, so we were given the entire information of the base flow. We have written, so first of all we looked into the regime of linear stability analysis. We have written equations that govern the total variables. Okay, and then we wrote the total variables as the base variables plus the perturbations. Okay, and then we saw that the base variables trivially satisfies the governing equations, for which now our objective is to calculate the equations which govern the perturbations. Okay, and and the approach is that we are trying to find out the equations which govern the perturbations by choosing non-dimensional variables, for which we have chosen these characteristic variables uh, as our scales basically. Okay. Now, once these characteristic variables are chosen, we know what to do next. Basically, we need to define the non-dimensional variables. So define non-dimensional variable. So as I said, all dimensional variables will be denoted by a star. So if there is no star, we will treat those variables as non-dimensional variables. Okay. For example, non-dimensional, the position vector is just the dimensional position vector divided by the length scale, which is h. The non-dimensional time is just the dimensional time, which is t star by tc, where tc, as you can see, is lc by uc. This is something that you can use. Okay. And the non-dimensional pressure is going to be P star by PC. Okay. And you can choose PC to be P naught basically. That is the base pressure. That is completely, up to you. Okay. And then my non-dimensional velocity is going to be my dimensional velocity by the characteristic velocity. Okay. So these are my non-dimensional variables. Okay. So these are my non-dimensional variables by choosing the appropriate characteristic scales. Okay. Okay. So then once we define the non-dimensional variables, the next the next immediate step is to write down the dimensional equations for the total variables in their non-dimensional forms. Okay. So governing equations for total variables, and by total variables I mean my total velocity and my total pressure in non-dimensional forms. Okay. For example, you can simply show that I will not do the intermediate steps because this is something that we have done repeatedly. So for instance, the continuity equation just boils down to the fact that divergence of the total velocity field is equal to 0, and the Euler's equation just turns out to be del V by del T plus V dot grad V equal to minus gradient of P. Okay. So these are the non-dimensional equations of the corresponding dimensional equations. Okay. By choosing the characteristic variables. So maybe I'll name these equations as what? Let's say 4a and 4b, where remember these are the equations for the total variable. Okay. Which means the total non-dimensional velocity field, this can be written as the base velocity field, but now it is non-dimensional in the x direction, plus the perturbations, which is v bar of, which is basically v dash of x bar t. Okay. And similarly I can write my non-dimensional pressure, and remember, see, this total variance, since the perturbations are a function of the coordinate and time, this makes the total variable also function of x bar and t. Okay. Similarly, my pressure is also, the total pressure is also going to be a function of x bar and t, and this is equal to, let's say, some base pressure, but it is non-dimensional, so we'll call it as p naught bar. Then remember, this p naught bar is constant because the dimensional base pressure is constant, and this can be written as p dash of x bar comma t, where, as I said, this p naught bar is the dimensional p naught divided by the characteristic pressure. And if you choose the characteristic pressure to be p naught itself, you can simply replace this p naught bar by just 1, because you have chosen the characteristic pressure scale as the base pressure itself. Okay. But without the loss of generality, we'll just call it as a constant, which is just some p naught bar. Okay. All right, so that's it. Then we have written, so what did we do? We have written the equations which governs the total variables in non-dimensional versions, okay, or in non-dimensional forms. And maybe I'll name this equation again as 5a and this as 5b. Okay. All right, I'll stop here for a couple of minutes And if there are any questions, please feel free to let me know. Okay. Okay. All right. So let's get back. So just for a recap, once again, what we did is we wrote equations for the total variables which involve the base variables and the perturbations. Okay. And then we said that the total variable is sum of the base variable plus the perturbations. And we saw that trivially the base variable satisfies the governing equations. And then what we did is, because we are trying to formulate the statement in a, or trying to solve the problem in a non-dimensional approach, we derived the characteristic scales that we had, and then derive equations for the total variables in non-dimensional form. Okay. So then, see, our ultimate objective, at least in the next, for the next couple of minutes, is to derive equations for the perturbations, we which means we now need to utilize the fact that we have equations for the total variables, and the total variables can be written as the base variable plus the perturbations, to look into a method for deriving equations for the perturbations. Okay. So our next step, that I'll call it as step 3 maybe, is to derive linearized, and I focus particularly on the word linearized, and we will see why. So we'll derive linearized equations for the perturbations. Okay. For that, what we'll do is we will just substitute these equations 5a and b. So we'll just substitute equations 5a and b into these equations 4a and 4b. Okay. So we'll substitute 5a and b in equations 4a and 4b, and then utilize the fact that the base variables already satisfy the governing equations. For example, if I substitute v bar as uz plus v dash, then I know that uz already satisfies the continuity equation. We already proved that, which basically means, so what in principle we are doing, we are actually subtracting the equations that the base flow satisfies from the equations of the total variable in order to get the equations of the perturbations. That's exactly what we are doing, and keeping in mind that the base variables trivially satisfy the equations. Okay. And if we do this, we will see that the continuity equation simply, the continuity equation simply turn out to be equal to divergence of v bar equal to 0, typically, because that's very simple, because if you just substitute this here, we already know that divergence of u of z is equal to 0. We already proved that before. That is, u of z trivially satisfy the continuity equation, which means that we will just end up getting divergence of v prime equal to 0. Okay. That's the continuity equation, and I believe now at least you can see that we have an equation. So we have the continuity equation which governs the perturbations. Okay. So this is basically, the continuity equation for the perturbed velocity field. Okay. And similarly, if you do the same exercise, that's exactly the same exercise for the Euler's equation. Let's try it out and let's try to derive the linearized. And by the way, this equation is already linearized because we know the continuity equation doesn't have, basically the incompressible version of the continuity equation doesn't have nonlinear terms. Okay. So then let's try to derive the Euler equations for the perturb variable. So that's all we'll do. We'll just substitute the total variable as the base variables for the perturbation. So the first term, which is del del t, sorry, the first term is del del t, but now we have, the base variable which is ux. And remember this u, I will not repeatedly write it down, but this u is just a function of z only. Okay, and we will have to consider this fact. And then I have plus the perturb variable which is v bar dash. Okay, that's the first term. The second term is, remember, it is v dot grad v, so this becomes u ex plus v prime, and then this is dot grad of u ex plus v prime. Okay, this is u dot grad v, and then I have minus gradient of pressure, which is gradient of p naught bar plus p prime. Okay, but I know that p naught bar is just a constant, which means this just simplifies to gradient of p prime. Okay, now let's try to look into the other terms. For example, if we look into this term, if we just look into this term is what? It is del del t of uex plus v bar prime. So I can then write it as del del t of uex plus del v bar prime by del t. But I know that my base flow is already steady, right? Which means that this term will simply go out to be equal to 0. Okay, so we just end up having just this term, which is del v bar by del t. Okay, similarly, if we look into this term now, this term is a little interesting one. Let's try to simplify it out. So what do we have? We have u ex plus v prime, and then this is we have then and then we have this dot product with gradient of uex plus v prime. Okay, so let's try to evaluate, or let's try to expand this term by term, and let's see what do we get. Okay, so the first term we'll get is uex dot gradient of uex. That's the first term. Okay, nice and slow. And then the next term would be uex, okay, dot gradient of v dash. The other term would be v dash dot gradient of uex. Okay, this is going to be the other term, and the final term would be v dash dot gradient of v dash. Okay, all right, now let's examine this term, because this simplifying this is actually important. First, let's have a look at this particular term. Okay, so what does this term say? This is basically u ex dot gradient, but remember gradient is del del x of uex. Okay, but I basically can also write it like del del y of uey and terms like that. But remember this u is just a function of z, right? Which means if I take a dot product, I just retain only the del del x terms, because this is where only we had the ex. And keeping in mind that u is just a function of z, means that this term is just going to be equal to 0, because del del x of a function which is just a function of z is equal to 0. Okay, means that this term, the first term uex gradient of uex, this term is simply going to be equal to 0, simply because the base flow is just a function of z only. Okay, however, this term is not going to be equal to 0, because we know that gradient of v prime, that is simply because of the fact that we actually don't know what is v prime. So v prime in general can be a function of x, this will be a function of y, this will be a function of z, as well as time, which means the dot product of this term is not going to be equal to 0, and we have to retain this term, and also the dot product of this term is also not going to be equal to 0, and we basically have to retain this term. Okay, so these two terms are then secured. Okay, this term is 0, these two terms are secured, that's well and fine. But this term is a problem. Okay, this v dot grad v is a problem, because see, remember we are trying to, so what we are trying to do in this analysis is we are trying to stick into something known as the linear stability analysis, which means we will only retain terms which are linear in the perturbations, okay, or linear in the unknowns, which are the perturbations. But this term, v dot grad v, this is a non-linear term in its perturbation, which means that in case of linear stability analysis, we will simply discard this term. Okay, so I'll write it down because this is important. So this is this term v dot grad v. Okay, this is a non-linear term, and we shall neglect it in the what to say, in the maybe domain of linear stability analysis. And by the way, this linear stability analysis in the literature of instabilities, this is typically known as LSA. So when we call LSA, we will understand that this, so the abbreviation LSA will understand that this is linear stability analysis. Okay, which then means that the Euler equation when written for my perturbation in the linearized mode is going to be del v bar by del t, that term is there, plus these two terms are going to be there because these two terms are non-linear. Why? Because the base flow is already known to us. Okay, which means this term have, so the only unknowns in this term is just this v dash bar, basically just the perturbed velocity field, which means that these terms are linear. I have to take care of that, and this term is basically neglected because it's a non-linear term, which means I just have del v dash by del t plus uex dot grad of v dash plus v dash dot grad of uex. These two terms are there, and then we have minus gradient of p dash for the perturbed pressure. Okay, so this is typically my linearized. So this equation is the linearized Euler equations which governs the perturbations, basically. Okay, so I'll write it down. So this is the, so this is linearized Euler equation which govern the perturbed variable v dash and p dash. Okay, where I believe you at least you need to have the sense that this v dash prime, this is basically it's so what is this? This is basically the perturbed velocity field, and you can write this as u dash ex plus v dash ey plus w dash ez. And the important thing is trying to appreciate that this u dash, v dash and w dash, these are these are not just functions of z, but they will be now functions of x, y, z and time, because we don't know anything about the perturbations. Okay, this is something that we're actually trying to solve for, which means we cannot assume anything on the perturbations. Okay, the only thing that we know is of the base variables. Okay, so similarly, v prime is also going to be a function of x, a function of y, a function of z and t, and w prime is also going to be a function of x, function of y, function of z and t. Okay, so that's it. We now have the equations, okay, which governs the perturbed variable. Okay, so what we'll do is we'll do one more bit of simplification. What we'll do is we'll write the equations. So we will rewrite. Maybe I'll name this equation. So the continuity equation is what? Maybe let's name it as 6a. Okay, and this equation we'll call it as maybe 6b. Okay, and what we'll do is we'll rewrite 6a and 6b in their component form. Okay, in that is the x component, y component, z component. That's all that we will try to do. Okay, we'll rewrite in their component form. Okay, so if you write the x momentum equation, let's see what the x momentum equation, that is the x direction of the Euler equation, let's see what it will turn up. For example, in the x direction equation, I will have this term. because this is a vector in the x direction, okay, which is basically pointing in the x direction. So I'll have a term from here which is del u prime by del x. That's one term that I'll have. Okay, so in x direction, yes, I will have the first term which is del u prime by del d, which is, so this u prime is basically the component of the partial velocity field in the x direction. Okay, I believe you understand this. Okay, this is something that we have shown here. Okay, so this is del u prime by del t, and the second term is going to be uz. So remember what was the second term? It was u ex dot gradient of v prime. So this will give you, so gradient of v prime is just going to give you del u des by del x ex, and then we have a dot product with ex. So the all other terms, that is ey and ez, those dot products will turn out to be 0, and we'll simply have this term which is u, which is a function of z, times del u des by del x. And the other term will be what? So remember, see, this term is gradient of u grad ex. Now, I believe you understand that this gradient of u grad ex, this will have a non-zero gradient because in the z direction only, because this u is just a function of z. Because in all other components, the gradient of this u in the x and y direction will turn out to be 0, which means that grad u will only be non-zero in basically in the z direction. Okay, because u is a function of z, which means this term will simply, you know, can be simplified as w prime times d of u by dz, and I believe you understood why this term remains from this term in the x direction. Okay, all right, and then sorry, and then I have the pressure gradient, which is just minus gradient of p prime del x. So that's it. That's the x momentum linearized Euler equation in basically in the x direction. Okay. Similarly, the y momentum equation, if you do that, you will basically get as del v prime by del t. That's obvious. In the y momentum, you are not going to have this term typically because this is just an, so basically this term is just a vector pointing along the x direction. So in y direction, this term is simply going to be equal to 0, but this term remains because this this v dash prime, this has components in sorry, I think I just wrote the other way around. So in yeah, so in y direction, this term remains, but this term basically goes to 0. Why? Because this gradient is only seen in the x direction typically. Okay, so so that's the other way around. Sorry for the confusion. So x momentum is okay. X momentum is not a problem. In y momentum, we will not have this term, simply because this has its direction in the x direction. So we will not have this term, but we will have this term. Why? Because gradient of v prime, you know, it basically has values. So gradient of v prime has values along x, y, and z direction. Typically, that's the idea. Okay. So this term is going to be in the y direction. It is going to be u of z times del v dash by del x. Okay. And this is equal to minus the pressure gradient is simple. It is del v prime by del y. And in the z direction, it is going to be del w prime by del t, okay, plus uz del w prime by del x equal to minus del p prime by del z. Okay, that's it. That's the component wise representation of the equations which governs the perturbations or the perturb velocity field u prime, v prime, and z prime. And remember, we also have the continuity equation. So the continuity equation is just trivial. It is just going to give you del u prime by del x plus del v prime by del y plus del w prime by del z. Typically because continuity equation is itself linear in v prime basically. Okay. So that's the continuity equation. And maybe we'll name these equations. So I'll name the first equation as 7a. I will name this as 7B. I'll name this as 7C, and I'll name this as 7D. Okay. All right. So these are the equations, okay, that we have. And maybe I'll stop here for a couple of minutes once again. You can quickly have a recap. I will just, try to clear why this term remains in x and why this term remains in the other direction y and z. See, this is trivial because in x, okay, I am basically going to have this term, and this term is also going to be there because u is a function of z. Okay, so I'll have a w prime dot du by dz, okay, in the x direction. But this term will not be there in the y direction, typically because this is 0 if we look into the y direction, okay, because the base flow because the direction of the base flow is only in the x direction, which means this term will only be non-zero in the x direction. It will be 0 in the y and z direction. But however, this term will have its signature in both in the three x, y and z direction, typically because this gradient of v prime, this will have del u prime by del x in the x direction. If we do a dot product with uex, it is also going to have del v prime by del x. If we take the y component and dot product it in the x direction, it is also going to have del w prime by del x. If we pick the z component form and do a dot product with uex, okay, that's the reason why we end up getting these terms u del v prime by del x, u del w prime by del z, and u del u prime by del x in x, y, and z. And in addition, this particular term appears in the x momentum equation, typically because of the fact that the base flow is in the x direction, and uh, its profile basically varies along z. That's the idea why we have this term, why we have this additional term in the x momentum equation. Okay, and this is a and the second thing is this is the ordinary derivative because we know that the base profile is just a function of z. Okay, that's that's one way of looking at it. Okay, that's it. Then what we have is, see, half of our task is done because we have derived equations which actually governs the perturbations, and now all we need to do is solve for these perturbations. For example, we'll solve for u prime, we will solve for v prime, we'll solve for w prime, and also we'll solve for p prime. Okay, so the unknowns that we'll solve for is u prime, v prime, w prime, and p prime. So these are the unknowns that we will solve. Okay, and we have four equations, so four unknowns and four equations, which means in principle this is a closed system. Okay, but it is not so straightforward to solve these to solve for these variables, because as you can see, these equations x momentum, y momentum, z momentum, and also the continuity coupled with the continuity, these are highly coupled. Okay, which means we require a certain specific strategy, okay, for solving this equation, and that strategy is known as normal mode analysis, and we will see why this is called as normal mode analysis. But I'll just take a quick break. I'll just come in 2 minutes by filling my mug with some water. Till then, you can have a quick recap at your end of the steps that we have done so far. Okay, I'll be back in 2 minutes. Okay, welcome back. So as I said, the next step now is basically to write down the perturbation in terms of their normal modes, and we will actually, you know, try to see that why do we basically do a normal mode analysis. See, one reason is that one possible reason for doing this technique of normal mode analysis is that, see, if we have a close look at equation 7, we see that there exists a trivial solution when u prime, v prime, w prime and p prime, they are all 0. For example, if we choose these to be equal to 0, we see that equation 7a going through to d are trivially satisfied, which means that these equations are homogeneous. Okay, so the idea of choosing normal modes is that the equations that govern the perturbations, and by perturbations I mean the perturbed variables, which are basically these. Okay, so the equations that govern the perturbations are homogeneous. Okay, and we will shortly see, maybe today or in the next class, that the boundary conditions of the perturbations are also homogeneous. Okay, which means that these two statements hints us that, okay, what actually we are trying to see or we are trying to solve is basically an eigenvalue problem. Okay, where we will see that since this is an eigenvalue problem, okay, because homogeneous equations and homogeneous boundary conditions are the perfect recipe for an eigenvalue problem, because it says that there exists a trivial solutions, but what we are trying to seek is basically solutions to the non-trivial case, where we will see that the perturbations will not grow or decay at arbitrary rates, but the perturbations, because this is an eigenvalue problem, the perturbations will grow or decay at very specific rates. Okay, and these things, that it's an eigenvalue problem which hints that the perturbations will grow or decay at very specific rates, these things hints that the solution methodology for finding out the perturbation will involve something known as the normal mode analysis. Okay, so I'll first write down the perturbed variable in terms of their normal modes. Okay, and then I will actually give you a flavor of why these normal modes basically come in this particular form. So the idea actually comes from Fourier series, and more particular in and more particular it comes from the knowledge of Fourier transform. Okay, but before that I will give you how to basically write down the perturbed variables in terms of the normal modes. Okay, for example, if I pick the x directional perturbed velocity, this I know is a function of x, y, z and t. Okay, this in terms of their normal mode can be written as some u hat, some function, and we will see that this is basically the eigenfunction. Okay, so this is u hat of z, and then this is multiplied with e power sigma t plus I times of kx plus ly. Okay, and I'll basically explain why this form of normal mode is taken. Okay, but trust me, let's first consider this, let's first write down these forms. Okay, and then we will see why do we take this. Now it is important to understand that this u hat of z, this is actually known as the eigenfunction. Okay, this sigma, this is the most important term in this expression, and this is actually called the eigenvalue. Okay, and this eigenvalue basically signifies to what we call it as the growth rate. Okay, so actually it is the sign of sigma, okay, which dictates whether the perturbations will grow with time or decay with time. Okay, and these quantities k and l, so these are known as wave numbers. Okay, so this is how you represent the perturbation in terms of their normal modes. Okay, maybe I'll call this equation as 8a. Okay. Now, before actually looking into the expression of v prime, w prime, and p prime in terms of their normal modes, I will first show you that how this idea of normal mode actually come into the picture. Okay. So maybe I'll quickly discuss something which so maybe it's a short note, that is the idea of normal mode analysis. Okay, that so you might, so the question that we are trying to answer is that why do we choose only this particular form as the normal modes? Okay, and we will see why basically we choose that. Okay, all right. So in order to get this idea, let's take, so this is a, so I believe you understand that the problem that we are trying to solve is a 3D problem. Okay, but in order to get the idea of this normal mode, let's solve a prototypical problem which is just, you know, a 1D perturbation problem. Let's, so which means that I have a flow whose you know, which basically have just one dimensional perturbation, which is, let's say, the x component of velocity, and the domain also is basically along x, meaning that I just have this quantity u prime of x comma t, where u prime is, let's say, the perturbed velocity in the x direction, and you know, x is my dimension, is my spatial dimension along x, and basically t is time. I am, for the sake of simplicity, I am just considering this 1D problem and neglecting the effects of y and z, because if this is clear, you know, extrapolating it in the y and z directions are very trivial. Okay. All right. So what I will say is that, so 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 basically, if I want to, you know, physically kind of draw the part, so if I want to physically, you know, draw the velocity, the total velocity field as a function of, let's say, x, okay, and if I want to plot the total velocity field, okay, I can then say that, okay, I have a fixed velocity, fixed base velocity, which I will call it as something like this. Let's say this becomes my u base, okay, and then I can have the perturbations. I basically have some arbitrary perturbations in my field, okay, and these are completely arbitrary. So these are basically my u prime of x, and they are also a function of time. So it's like on one particular time stamp, my perturbations basically vary something like this on the x, which means that if I add this and this, I basically should get my entire velocity, the total velocity, which in principle is a function of x and time. Okay, so then what we say is that, since, you know, this is an eigenvalue problem, as I said, I basically say that my perturbations, let's say u prime of x comma t, this is equal to some u tilde of x, which happens to be my which happens to be the eigenfunction, times e power sigma t. Okay, where sigma, as we say, is nothing but the growth rate. Okay, so writing the perturbations in this form is testimony to the fact that this problem is an eigenvalue problem. So I know that whatever, so since this is an eigenvalue problem, I know that the term which signifies that the perturbations are going to decay or, you know, grow with time is going to be this e power sigma t. Okay, and this u tilde of x is nothing but the eigenfunction corresponding to the eigenvalue sigma. Okay, now the point is, how do we then write this u tilde x? This is the next question. Okay, so for this we take the help of Fourier series, and more importantly the Fourier transform. Okay, so then we'll try to write u tilde x. Now from the knowledge of Fourier series, we have discussed this principle when we are learning separation of variables into solving, you know, the Navier-Stokes equation, the multi-dimensional form of the Navier-Stokes equations. We saw that if we have any arbitrary function, let's say along x, you know, where x basically varies from -1 to 1, but so what we saw is that if, let's say, we have an arbitrary function of x where x varies from -1 to 1, I can then effectively write f of x as something like a naught by 2 plus sum over k equal to 1 to infinity, or k, okay, k equal to 1 to maybe infinity, ak cos kx plus bk sin kx. Okay, Now, what does it say? It says that if I have my x varying from, let's say, -1 to 1, or in principle this x should be varying between -pi to pi actually. Okay, if we were to represent this in this form. So it says that if I have my x varying from -pi to pi, I can represent any function in x by using bunch of sine and cosine. Now, since this domain of x was a discrete domain varying from -pi to pi, okay, I mean it's a bounded domain where I know that x only varies from -pi to pi. I basically say that the contribution from the individual modes or from the individual wave numbers can be written using summations. But now think of the fact that what happens when the left and the right bound basically goes from -infinity to infinity, which is the case of the flow problem that we are solving, because we said that my x is basically a domain where the length of the domain basically varies from -infinity to infinity. So then what we do is, instead of summing up, this is the important concept, okay, instead of summing up the wave numbers, what we do is we integrate, instead of summing up this expression, we integrate this expression with respect to the wave numbers. Okay, meaning that I will write this u tilde of x, okay, as some ak, as a bunch of sine and cosine, just like how we have written it here, which is some ak sine kx plus some bk cos kx maybe. Okay, but now instead of summing them up from k equal to, let's say, 0 to infinity or 1 to infinity, what we'll do is we'll integrate them with respect to dk and then integrate it from 0 to infinity. Okay, so what does it mean? It says that now instead of having discrete wave numbers, it will basically have all the wave numbers, because my domain now basically varies from -infinity to infinity. Okay, and this is the idea of Fourier transform. Okay, this is Fourier series. So the for the discrete domain, this is the one we call it as Fourier series. And this, the thing that we have written on the left, this is actually known as Fourier transform. Okay, now what we'll do is we will use the fact that you can write sine kx as e power I kx minus e power minus I kx by 2i, and you can equivalently write cos kx as e power I kx plus e power minus I kx by 2. And then what you need to do is you just need to do a change of variable in one of the integration, where you can choose a k bar which is equal to minus k. You just need to do this change of variable in one of the two integrations after substituting these two things in these forms. And then I'll not do the steps, because I know this is beyond the scope of this discussion hour, but that's the idea. What you need to do is just need to substitute that sine kx is equal to this, cos kx is equal to this, and in one of the integrals you need to change, to do this change of variable. And then eventually when you do this, you will see that your u tilde of x, this can be written as integral minus infinity to infinity some ck e power ikx dx. Okay, this is how precisely the form of u tilde is chosen. Okay, so therefore my then see, this is just u tilde of x. Okay, but remember, I also need to calculate something known as the total perturbation, which is u prime of x. So u prime of x comma t, if you remember, it is just u tilde of x times e power sigma t. Okay, and then this u tilde of x is integral minus infinity to infinity. Okay, and I think I made a mistake. So this is, remember, this is dk. Okay, this is not dx. This is just dk. Okay, because these are dk's basically. Okay, so this is dk, and then this is ck times e power ikx dk. Okay, and then I have e power sigma t, which means that this u prime of x comma t will basically be equal to what? So this is u prime of x comma t is equal to integral minus infinity to infinity ck e power sigma t plus ikx times dk. So this is how, okay, this is how you basically write, the perturbations using Fourier transform. But remember, we have not used the concept of normal modes here, and we'll basically look how does the concept of normal mode appear. Okay, so this is how you represent a 1D perturbations, a 1D perturbation using Fourier modes basically. Okay, and Fourier transform. Now the idea is that, so the idea of normal mode is as follows. Now we know that since sine and cosines are orthogonal functions, that means each mode, this is important, okay, and we have learned this also in separation of variables. So each mode behave independently of the other. Now since each mode behave independently of the other, what I can do is I can represent, so instead of writing the integral, I can represent this u prime of x comma t as ck e power sigma t plus ikx. Okay, and I can do this because I know that the kth mode behave independently to the other modes. For instance, the kth mode will do its own job, the L mode will do its own job, and so other modes basically. Which means, instead of writing the expression for all the modes, if I can pick a generic mode and write the expression for u prime, I know that for all other modes this expression from u for u prime will remain intact, typically because I know that the modes behave independently. And this idea of not writing the summation and writing this for any generic mode k, this is actually known as normal mode analysis. Okay, the name normal suggests that the name normal also means orthogonal. So to what we have learned in separation of variable, it suggests that every mode will do their own job, and that's why instead of writing the integral, we can write the expression for just one generic mode. And this is the basis on which we have written this expression for u prime basically. Now the idea is, here we have two directions, so we have unboundedness. So if you look into the picture, we actually have unboundedness along x and z, because see, the domain is bounded along z, so this means I cannot have all the wave numbers along z, but the domain is unbounded along x, it is unbounded along y. That's the reason why I have wave numbers k along x and l along y basically. Okay, that's the reason why I believe you can now understand that why did we actually have ikx plus ly. So earlier we just had ikx because it was just a 1D problem where we just had unboundedness along x. But now we have unboundedness along x and unboundedness along y. And that's the reason why we have this term ikx plus ly. Okay, and this term is simple. It's the sigma. It's e power sigma t, and this is typically the eigenfunction. Okay, that's the basis of how this normal modes actually can be written. Okay, all right, then let's quickly write down the other part of components as well. So for example, we can then have v prime. Okay, for example, we can then have v prime of x comma t, and this is equal to v hat of, this is simple, just how you have written u dash. This is going to be equal to v hat of z, sorry, times e power sigma t plus ikx plus ly. Okay, and then I have w prime of x comma t is equal to w hat of z times e power sigma t plus ikx plus ly. Okay, and also we need to write for the pressure, that is p prime of x comma t is going to be some p hat of z, okay, times e power sigma t plus I times of kx plus ly. Okay, so that's writing all the part of velocities and the part of pressure in terms of their normal modes. Okay, maybe I'll call this equation as 8b, and this is 8c, and this is 8d. Okay. And then what we'll do is, I said that this sigma, this is basically the eigenvalue that we will actually try to solve for. This is the eigenvalue. So for this problem, what I'll do is, I'll do a quick transformation. So I'll write sigma as minus I alpha c, where my alpha is equivalent to the wave number k, and I'll also define something known as a beta, which is equivalent to the wave number L. So it's basically like the wave number along x, I have denoted it as alpha. The wave number, any generic wave number along y, I'll denote it as beta. Okay, and then what I can do is, I can then say that C is equal to some real part of CR plus I times CI, just like writing some complex number Z as, x plus IY. I have just written C as CR plus CR plus I times CI, where CR, so basically CR is the real of this C, and CI is the imaginary now part of C basically. And then I can then write sigma as maybe I alpha times CR plus I times CI, which means this is minus I alpha CR plus, because minus I square is going to be equal to just 1. So this just becomes plus alpha times CI. Okay. So now the term e power sigma d, which basically signifies the growth rate, I can then write it as e power alpha ci minus I alpha cr, because this was sigma and then this is t. So then I can then rewrite it as e power alpha cit e power minus I alpha cr t. Okay. Now here is something that is very important. See, I don't actually need to bother about this term, because I know that e power I theta is going to be just cos theta plus I sin theta. Okay, so this term is not going to exponentially rise or decay based on time, because I have an I here. These are just going to be cosine and sine functions. But what is interesting is actually the dynamics of this term. Now see, if we just look at this term e power alpha cit, now if alpha ci is greater than 0, and this means that since we know that wave numbers are always greater than 0, this equivalently means that ci is greater than 0, then I can say that this term is going to exponentially rise with time or exponentially increase with time, which means that my perturbation, so what does it mean? This means that if I add a perturbation, the perturbation will basically grow with time. So the condition of ci greater than 0 says that my perturbation says that I have an, so basically it signifies instability, which means that my perturbations will grow with time. And how they will grow? They will exponentially grow with time. Okay. On the other hand, alpha ci less than 0 means that this quantity is going to be negative, which means that ci is basically less than 0, and it says that this is a stable system, which means that my perturbations, if you add a perturbation to the base state, they will basically decay with time. Okay. So this means that my perturbations will decay in time. Okay. So that's it. These are the two conditions that we will have, which will say, so eventually after finding out the eigenvalue and basically the quantity ci, okay, the sign of ci is just going to dictate, and it is just going to tell me that okay, which mode. So we will see that these c's are basically functions of the wave numbers as well, and we will see that which wave numbers basically grow with time and which modes basically decay with time. Okay, and this is very important because it signifies or it tells about the stability of the system. If ci is less than 0, we will see that perturbations will decay with time. If ci is greater than 0, we will see that perturbations will grow with time. This basically signifies stability. So ci, the sign of ci in principle signifies stability. Okay. Okay, all right. So what we'll do is we will stop here for today. We will not go into the next step. So I believe you can now understand the next step. So what we'll need to do is we'll substitute the normal modes into the equations which govern the perturbations to basically get the ultimate governing equations, which we will see. So we'll apply one more principle. or theorem. Basically, it's a theorem which is known as the squares theorem. So after substituting and applying the squares theorem, we will see that you can effectively reduce the problem into a 2D problem, from which you can use the stream function and then eventually derive the Rayleigh stability equation. Okay, but we will do this in the next class because it's not possible to finish all of this in one go. But I believe you have understood the essence of this problem. What we did, like just giving you a quick recap, we started off by actually writing equations for a total variable dimensionally. Okay, then what we did is we found out that the base flow satisfies the equations trivially. Okay, and then what we did is we non-dimensionalized the equations, and then using non-dimensional variables we wrote the equations which govern the total variables in non-dimensional form. Okay, and then what we did is derive linearized equation for the perturbed variable, staying in the realm of linear stability analysis, which we call it as LSA. And then what we did is the most important part is that, right, is identifying the fact that the equations which govern the perturbations are homogeneous, and so is the boundary conditions. We will see that very shortly in the next class. And then realizing that this is an eigenvalue problem, which means that the perturbations, if they exist, they will decay or grow in very specific manner, which hints us that this is an eigenvalue problem that we are solving, which means we need to look into something known as normal modes. Okay, and then the idea of normal modes comes from the fact that since my domain is infinite, I can construct a function which are nothing but the perturbations using sines and cosines. But now, since the domain is infinite, instead of having discrete wave numbers, I will have all the wave numbers that is present, and we use the concept of Fourier transform to basically write the normal modes of the corresponding perturbations. This is something that we have seen up to today, and I believe just from this exercise that you can appreciate how rich perturbation analysis is, and how much I mean how much things, or how much nuances we can basically dig from doing this kind of exercises. That's the reason why I feel that this is the most important module, as I was telling in the beginning, that is this is the most important module of this of this course, because it gives you tremendous insight. It involves maths, it involves physics, it involves fluid mechanics, and it just gives you so it just have basically recipes of everything, like Fourier series, orthogonal functions, linearizing systems, and also the fluid mechanics part as well. Anyways, so what we'll do in the next class is we'll just substitute the normal modes that we have derived into the governing equations for perturbations to derive basically equations that govern the perturbations. Okay. Okay. All right. So let's stop here for today, and we will meet in the next week, and we'll carry. We'll take it up from where we have left. Okay. In the meantime, if you have any question, please feel free to post your questions in the discussion forum, and we'll be happy to address them. Till then, thank you, and we'll meet in the next week. Thank you very much.